Welcome to this explainer. Today, we're stepping right into a classic chemical detective story. We're going to take a pretty fascinating journey from the macroscopic right down to the microscopic. We'll start with this dazzling visual phenomenon you can actually see with your own eyes, and then we'll drill all the way down into the invisible transfer of electrons that literally makes it happen. It's just a perfect blend of striking lab results and elegant chemical theory. Okay, so here's our structured roadmap for today. We're going to cover the silver mirror phenomenon, preparing Tollens reagent, the actual laboratory procedure, the redox reaction mechanism, aldehydes versus ketones, and we'll wrap up with some A-level exam success tips. Let's dive right in. All right, section 1, the silver mirror phenomenon, visualizing the test. Picture this. You're standing at a lab bench. Have you ever seen an ordinary, simple glass test tube suddenly, and I mean almost magically, coat itself in a beautiful, flawless layer of shiny silver? It is hands down one of the most famous and visually stunning reactions in all of organic chemistry. But hey, it's not magic, right? It's just chemistry at work. This whole phenomenon is officially known as Tollens Test, though you're probably going to hear people call it the silver mirror test for pretty obvious reasons. Basically, it's a chemical test that uses a very specific solution, ammoniacal silver nitrate, to tell apart two closely related types of organic compounds, aldehydes and ketones. Think of this test as our primary investigative tool to interrogate an unknown chemical suspect, based entirely on whether or not it can be oxidized.
Moving on to section 2, preparing the reagent. Freshness is key.
Now, whipping up this reagent takes a really precise 3-step sequence. First step, you take a standard silver nitrate solution. Second, you drop in just a tiny bit of sodium hydroxide. Instantly, boom, you'll see this brown precipitate of silver oxide form right in the tube. Third, you carefully add a dilute ammonia solution, drop by drop. And as you do that, the brown precipitate just dissolves, leaving you with a perfectly clear, colorless solution. That clear liquid holds the all-important diamminesilver ion complex. And there you have it, your freshly prepared Tollens reagent. But here is the absolute crucial point. You must never, ever store this reagent for later. Seriously, this is a massive laboratory safety rule. If you just leave it sitting around, old Tollens reagent can actually produce highly dangerous, explosive silver compounds like silver nitride. No joke. So you always make it fresh right before you need it, 0 leftovers allowed, and you dispose of the whole shebang immediately after your experiment is finished. All right, section 3, laboratory procedure, testing the unknown. The actual physical procedure, it's remarkably straightforward. First, you take about 2 cubic centimeters of your unknown organic compound. Next, you add an equal volume of that freshly prepared Tollens reagent we just made together. Finally, and this is a big one, you warm the mixture gently. But wait, you must warm it in a hot water bath. Never ever heat this mixture directly over an open flame. Once it's chilling in that warm water bath, you simply sit back and observe carefully. Now check out the dramatic visual contrast in our possible outcomes. If your mystery compound is an aldehyde, jackpot, you get a positive result. A shiny silver mirror forms right on the inside glass of the test tube. Sometimes it might look more like a gray or black deposit of metallic silver instead of a perfect mirror, but both of those mean a positive test. On the flip side, if your compound is a ketone, negative result. Absolutely no visible change occurs. The solution stays completely colorless and no mirror forms. Which brings us to section 4, the redox mechanism, electron transfer. This perfectly illustrates the true chemical heartbeat of the entire experiment, because inside that tube, we've got 2 things happening simultaneously. The aldehyde is undergoing oxidation, meaning it's losing electrons and transforming into a carboxylate ion, which is essentially a carboxylic acid. And at the exact same time, these silver ions are undergoing reduction. They're grabbing those lost electrons and transforming into solid metallic silver. Since oxidation and reduction are happening as a pair here, this is officially classified as a redox reaction. Take a look at the balanced general equation that maps this all out. Over on the left, we have our general aldehyde, written as RCHO, reacting with our diamminesilver I complex ions and hydroxide ions. Now track across the arrow to the products. See how the aldehyde has morphed into the RCOO- carboxylate ion? And right next to it, look at that 2Ag. That right there, that is the literal birth of our solid metallic silver mirror. Let's actually ground this complex equation with a specific real-world example so it clicks. Let's say our unknown compound is ethanol. It gets oxidized directly into ethanoic acid, or an ethanoate ion, since we're in an alkaline solution. Meanwhile, those silver ions step up and gain the electrons the ethanol just tossed away, becoming solid silver metal. It's this exact one-to-one chemical handshake that triggers that beautiful mirror effect on the glass. Next up, Section 5. Aldehydes versus ketones. Structure matters. To really grasp why this happens, we have to visually pit their molecular structures against each other. Okay, so both contain a carbonyl group, but here's the kicker. In an aldehyde, that carbonyl carbon is exposed. It's attached directly to a hydrogen atom. A ketone, on the other hand, its carbonyl group is buried right in the middle, securely wedged between two other carbon atoms. There is no attached hydrogen. And that specific structural difference, that is the aldehyde's ultimate vulnerability. Because ketones are missing that directly attached hydrogen atom, they just cannot be easily oxidized under the mild conditions of our warm water bath. And hey, if the ketone can't be oxidized, it can't force the silver ions to be reduced. Without that electron transfer, the silver stays totally dissolved in the solution and absolutely no mirror forms. So, the structural detective work perfectly explains the physical result we see in the lab. Finally, Section 6, A-Level Exam Success Tips. Maximize your marks. Okay, here is your rapid-fire cheat sheet of mandatory observations. This is exactly where students always seem to drop marks by being just a little too vague. When you write about this, you absolutely must specify that the reagent is fresh. You gotta know it's ammoniacal silver nitrate, containing the diamminesilver ion, and when they ask for observations, please don't just write every X. You need to explicitly write down shiny silver mirror or gray deposit for a positive result and no visible change for a negative result. Finally, always be ready to identify the purpose, which is distinguishing aldehydes from ketones, and the reaction type, which is oxidation reduction. Hit those points, and you've pretty much mastered the topic. So we've seen how a difference as incredibly tiny as a single attached hydrogen atom determines whether a solution stays a boring, colorless liquid or transforms into a stunning, reflective silver mirror. It kind of leaves you wondering, doesn't it? If such a minuscule, totally invisible structural detail can create such a dramatic physical outcome in a simple test tube, what other invisible chemical differences are silently shaping the physical world all around you every single day? Keep exploring, keep questioning, and I'll see you in our next explainer.